first part is regarding preparation. So for preparation, we need to have a few things, a few items. So in general, what we need is a hard hat, because we go to the site. Optional, we can have some goggles to protect our eyesight. And then we need to have special electrical gloves. So this is actually rated at 1 kV. The gloves, not the normal gloves, because we are going to deal with live condition. And we also need our trusted meter. Okay. And apart from that, the documentation that we need is we need to have information on the module, and then we need to have the information on the schematic diagram, and we need to have the datasheet on the inverter. Okay, so now I'm going to demonstrate to you before we do the checking or the testing and commissioning. So we need to wear our PPE. So to wear our PPE, we just put on the hard hat and make sure that before we put on our gloves, if we have some jewelry or items on our fingers and hands, and now I'm wearing my watch, so I need to open it. Okay, if you are wearing, let's say, rings or bracelet, you need to open them before you wear your electrical glove. Okay. So after this, we are going to go to the system and see how the testing and commissioning process is done. Right. Okay, so this is the schematic diagram for the system that we want to assess. So it has, we move from the left to the right. So the center is the inverter. So we have 8 panels that is forming one string, and from the PV modules, one string, it goes into the DC fuse. DC fuse, it goes into the main switch, and then from main switch it goes to the inverter, input inverter, right? And in between we have DC SPD. So if you recall, SPD is surge protective device. Its function is to protect the inverter from lightning surge. So if there is lightning strike at the module, then the voltage will travel along this line here, and it will be captured by DC SPD. Okay, so after the inverter, for the fuse and the main switch, a fuse will trip if there is overcurrent. It will blow if there is overcurrent, and main switch, we can use it to do maintenance. So we need to remember that and even when the main switch is off, there will always be power coming from the PV module if there is daylight, if there is sunshine. So we need to be careful. There's still life, no matter what you do at the main switch. Right. Coming out of the inverter, so we have AC supply now. So we connect it to the AC MCB, AC SPD, okay, parallel as well to protect if lightning comes from the other side, and then PV meter, and then main switch before it goes to the grid. Okay, so now after this we are going to look at the system to see and match them with what we see from our single line diagram. Okay, now from single line diagram, this is what is the actual configuration in the array junction box. So for this one, because it's already completed, you can already see the labels. But if you do not see the labels, you should also be able to identify. Okay, so these are the cables from the solar panel. The way that you can know it is from solar panel is the cable itself is different. You can see the cable is quite thick and it's dark in color. And this is usually DC cables, solar cables that is used. Okay, and then from solar panel DC, the wiring goes to the DC fuse. So here we have 3 inverters. So we have 3 fuses, 3 systems separate. From the fuse, it goes to the DC MCB. From the DC MCB, it goes to the inverter. So here we have inverter DC. So the wiring goes to the input of the inverter, and then it's going to be parallel with the surge protective device, DC SPD. Okay, then coming out of the inverter, so we have the AC side of the inverter, and then from the AC side of the inverter, it goes to the AC MCB parallel with AC SPD, and then it's going to be connected to the main switch outside of this box, and then connected to the grid. So this is the configuration. Now, the condition for all the protective device now, as you can see, is in off mode. The DC MCB is off, the AC MCB is off, and the fuse is open, meaning it's an open circuit. But we need to be careful because the supply coming from the solar panel is still energized, because right now I'm taking this video during daytime. So if I were to measure using this meter, I measure between positive and negative for one string. So you see that the voltage given is 267 volts for one string, for one inverter. So we need to be careful that even though we have turned off the system, there is always going to be live voltage coming from the PV, as long as there is sunshine. Okay, now I want to demonstrate to you how to turn on a PV system for operation for the first time. Okay, just now I measured the voltage here, so I'll show you again. So the voltage measured is 200. Now it's 266. Oops. Maybe okay, 266. Okay, so first thing we need to do is we check this voltage to make sure that the voltage does not exceed the maximum inverter voltage. Now from the data sheet, I already know that the inverter has a maximum voltage of 700 volts. So this one is 267, so well below the maximum, so it's going to be safe for us to turn on. If when we measure the value is larger than 700 volts, then we should not turn it on because it can damage the inverter. Okay, so the sequence or the step to turn on, we always start from DC to AC. Okay, so turning on, we start from DC to AC. So now I will put in the DC fuses. I'm just going to do for one phase, so I'm just going to do for the left side. So I turn on the DC fuse, and then I turn on the DC MCB. Okay, so after I turn on, if you look at the inverter after some time it should start. So there will be some delay, I believe. Okay, now the indicator light is blinking. Okay, so now you can see the reading from the inverter. So you see that this is the image for the module. The voltage is 267, same as what we measured just now, and the current is 0. Okay, the power is also 0, and the AC side is open circuit because we haven't connected the AC side yet. Okay, so now we are ready. So now we go back to our junction box. So after we turn on the fuse and the DC MCB, now we turn on the AC MCB. And we wait for a while. So the sound that you hear is the sound of the inverter synchronizing itself with the grid. So it's going to check the value of the voltage and the frequency of the grid. If it matches, then it will connect the inverter. If it does not match, then it will not connect with the grid for safety purposes. Alright, so now if you move back and you see the inverter data or the inverter display. Okay, so for PV, one of the ways that they design the inverter is that when you tap, the indicator light will turn on and you can see better. So this is the DC side, this is the AC side, and this is the current instantaneous power that is produced now. Right? So if I tap again, then it's going to change from current. I tap again, I can get the voltage. So this is the standardized design for inverters on site, for you to be able to read them easily. Okay, so this is how you turn on the system for the first time. Okay, now I want to demonstrate about what we call as anti-islanding. Now, to recall, anti-islanding is when the power from the grid is off or is not available or is out of range. We want our inverter to cut off the supply. We do not want our inverter to supply to the grid under those conditions for safety purposes. Okay, so now the system is turned on. So let us measure the DC voltage. Okay, the DC voltage is now 217. Okay, now AC voltage, I measure at the output of the inverter. The value is 251 volt AC. Okay, our standard single phase is 240 or 230, right? So in U10, because we are close to the substation, so our voltage is a bit higher to compensate for the voltage drop when the cable goes out from our transformer to nearby areas. So it's a bit higher, but still within normal range. Okay, so now we want to make sure that when there is a grid problem, our inverter does not supply. How do we simulate that? So anti-islanding, we simply turn off the AC MCB and verify that there is no power coming out of the inverter. Okay, so now I am going to turn off the MCB because now the circuit is energized. Alright, so if you look at the inverter now, the inverter is generating 533 watts. Now I'm going to turn off the AC MCB. Okay, I am now simulating a loss of supply from the grid. So you see that instantaneously, once I turn off the AC MCB, the light starts to blink and the power drops to 0. Right? This means now that the inverter no longer supplies power to the grid. But there is still power at the DC side. Now if I measure back at the inverter input and output, I measure the DC part, I still have a value of 266 volts. This is the input voltage coming from the module. But now, if I measure the AC side or the output of the inverter, the value is 0. Even though there is power from the solar panels, it reaches the inverter, but it does not come out of the inverter. Why is this? It's because when the grid supply is off, we do not want our PV system to supply power because it might be dangerous. Let's say TNB is doing maintenance at the line because of the fault. So if we supply power, then the technician will not know there is power coming from our PV system, and it can injure them, or in worst case scenario, it can even kill them. So that is why this concept is called anti-islanding. We do not want our PV systems to become their own islands and generate power to the grid without the knowledge of the grid operator.